may I introduce our first speaker in this session. This is Lidya Tarhan from Yale University, all the way from the US, so the floor. You know what you're doing.
Yes.
And 2 minutes, I can do one.
Yes, thank you. All right, thank you. Thanks for sticking around so long. So the Ediacara biota is Earth's earliest fossil record of communities of complex, macroscopic, multicellular organisms. And Ediacara biota fossil assemblages occur around the world in rocks of terminal Neoproterozoic age, so from about 580 to 540 million years ago. And these organisms were, almost without exception, entirely soft-bodied, which makes their fossilization, and especially their Ediacara-style preservation as casts and molds, as three-dimensional impressions in sandstones, particularly enigmatic. What these organisms were, where they fall in the broader tree of life, remains in many instances cryptic, but we do know that these organisms were complex, both morphologically and ecologically, and that these assemblages record a number of important firsts on the march toward complex animal life, such as the earliest movement, the earliest sexual reproduction, and at the very tail end of the Ediacaran, the earliest biomineralization. And one of the particularly distinctive aspects of the Ediacara biota is that in situ assemblages of these enigmatic macrofossils occur alongside what we term textured organic surfaces, or TOS. And TOS are dense, diverse, patterned organosedimentary textures, which we interpret to record the interaction between organically bound seafloor sediments, so mat grounds or biofilms, and mechanical sedimentary processes. And as you can see here, the range of structures that falls into this broader category of Ediacaran TOS is quite large. And many of these structures are, in fact, so large and so morphologically differentiated that we consider them to represent dense assemblages of multicellular eukaryotes. So a very different picture than what typically comes to mind when we think about modern prokaryote-dominated mats. And TOS are significant because they record the manner in which mat grounds shaped the benthic ecology of Ediacaran communities. In other words, it's long recognized by workers such as Dolf Zeilacher, who came up with entire classification schemes to explain this pattern. The morphology and the substrate interactions characteristic of Ediacara macrofossils appear to reflect in large part adaptation to a mat-ground-bound world. So for instance, the iconic Ediacara macrofossil Kimberella is typically associated with fan-shaped arrays of radiating ridges, which you can see depicted here, which are analogous to the rasping structures of modern gastropods. And this association has in large part driven interpretation of Kimberella as a potential stem mollusk. Other Ediacara macrofossils appear to have made a living encrusting the upper surface of mats, stabilizing themselves by immersing themselves within mat grounds, or to have derived nutritional matter from mats via undermat mining. And the presence of pervasive and diverse mat grounds appears to have shaped not only the ecology, but also the environment, the habitat in which Ediacara organisms lived and died and entered the fossil record. And this is particularly true of the Ediacara Member of the Rawnsley Quartzite of South Australia, which is the unit for which the Ediacaran period is named, and which contains the most diverse Ediacara fossil assemblages. And for the remainder of this talk, I'm going to be focusing upon one facies in particular of the Ediacara Member, which we term the oscillation-rippled sandstone facies, which consists of mature, fine to medium-grained, symmetrically rippled sandstone tempestites, which we interpret to have been deposited between fair weather and storm wave base. And the data that I'll be showing are derived from sequential bed-by-bed excavation of this facies and reconstruction of these sandstone bedding plains at a number of localities to the west of the Flinders Ranges. So one of the features that sets the oscillation-rippled sandstone facies particularly apart is that it is texturally homogeneous. All these beds are fine to medium-grained sandstones, and in fact, over 50% of adjacent bed pairs are utterly indistinguishable in terms of grain size or other textural properties. Also, in terms of thickness, this is a thinly bedded facies, as you can see here. Although beds may be as thick as up to a decimeter in thickness, the majority of these beds are incredibly thin, sub-millimeter to millimeter scale thicknesses, in spite of being fine to medium grained sandstones. And we term these especially thin bed form shims for their resemblance to industrial shims. And these shim scale, sub-millimeter to millimeter scale bed forms are also characterized by a striking lateral discontinuity. They typically, to the extent that we've been able to excavate them, range only up to square centimeters to square meters in area coverage, whereas beds at the thicker end of this spectrum may range up to square decameters. Another striking aspect of this facies is that these sandstone beds tend to be doubly rippled. And by that I mean that the upper surfaces of almost every bed in this facies are symmetrically rippled. But the undersides, the basal surfaces of these beds, even our sub-millimeter scale shim bed forms, crisply cast the underlying rippled upper surfaces. So as you can see here by this part-counterpart pair, here's the rippled upper surface of one of these shims. Here is the counterpart, the base of the bed that overlay it. Moreover, there's a lack of any evidence for erosion in this facies. There are no erosional bed junctions. And in spite of their textural uniformity, these beds remain discrete. They are not amalgamated. These shim-dominated successions are also characterized by an unusual preponderance of textured organic surfaces. And in fact, there appears to be an inverse correlation between how dense, how laterally extensive, and how thick these toss are and how adhering these bed forms are. Where you have thicker, better developed toss, your bed forms are less adhering. Where there's less toss, they tend to be more adhering, less easily excavated. These shim-dominated successions are also characterized by very high abundances of helminthoidic gnites, the bilaterian grade burrow that has been interpreted to reflect undermat mining behavior. And in terms of Ediacara macrofossils, this is the facies that is richest in Ediacara macrofossils, which occur along these sandstone interfaces as part-counterpart pairs. And again, there is no dissimilarity in terms of grain size or other textural properties between these parts and counterparts. These Ediacara-style macrofossils are preserved exquisitely in both part and counterpart with no intervening lithology. And we recently proposed that this distinctive style of preservation was mediated by the early diagenetic precipitation of silica cements from ocean waters that were rich in silica prior to the evolution of silica biomineralizing organisms. So if we consider all of these sedimentary features in tandem, the lateral discontinuity, the extreme thinness of bedding, these doubly rippled bed forms, textural homogeneity, and also the preponderance of toss and helminthoidic gnites burrows, characterizing these sandstone successions, we start to get a very unusual picture of the Ediacaran seafloor, and we can liken this record to microbial mat sandwiches, hence my title, in that what we seem to be capturing are alternating episodes of storm-mediated sand deposition and interdepositional intervals of colonization of the seafloor by macrounds and macroorganisms. And this distinctive combination of sedimentary features indicates that the sediments were organically stabilized to the extent that they prevented erosion or reworking or even ripple migration and promoted the detailed capture of even very thin depositional events as discrete bed forms, as well as the exceptional fossilization of these macround-associated communities. And these continuous stacks of event deposits appear to constitute a complete record of deposition and community development along the Ediacara seafloor. And the hiatuses characteristic of this record, if we can even use that term, are not geological in scale. They're ecological and are represented by those intervals of community development between episodic storm deposition. So in conclusion, the sedimentary and paleontological features of the Ediacara member appear to record a strong role for macgrounds in mediating the ecology as well as the habitat of Ediacara organisms. Macgrounds stabilized the substrate, which likely promoted the colonization by these organisms in even high-energy seafloor settings, as well as promoting the development of unique benthic life modes on the part of the macroorganisms. And this distinctive set of sedimentary features and unique style of stratigraphic packaging, so uncharacteristic of modern or Phanerozoic sandy storm rework settings can, I think, even in the absence of organic remains and even in the absence of toss or mist, be used as a metric in deep time geologic successions for the presence of organically bound substrates. Thank you, and I'm happy to take any questions.
Sam, a quick question. Yeah.
How do you explain then why adjacent beds haven't been amalgamated by cementation? If there's nothing separating adjacent beds, it's got exactly the same sediment in it, why hasn't cementation amalgamated them?
Well, I think that what is separating those adjacent beds are microbial mats. And some of these may have been very thin, may have been biofilms. So I think that in tandem with perhaps this early silicification mechanism that we think is responsible for the preservation of the macrofossils may be promoting this exceptional style of sedimentary record.
So you're implying that the silicification would have been before the decay of the microbial mat?
No, I think it was coeval with the decay.
Okay.
That's great. Okay, well, thanks again.